So, hello everyone. Thank you for coming to this session. My name is Ken Kuano. I am a software engineer and developer relations at Epic Games Japan. Let's start my presentation with this title. It is important to note that the features introduced today refer to UE 5.4. They are not yet production ready or have been released as beta versions. Please keep in mind that the configuration and architectures described here may change in the future. Similarly, I am referring to measurements which may be further improved in the future. First, I'd like to give you an overview of this session and conclude with a few words. By editing this session, you will be able to do the following things: gain a better understanding of the future that can improve your development iterations, accelerate routine iterations such as cooking and packaging by applying them to your projects, check it quickly on the target device and save time to adjust the look and feel. Consider yourself the best solution for your project. We want to introduce you to the various features that can improve your development iterations. Well, I'll be sharing with you about the background of why we need to improve the iteration in UE5. The game industry is changing significantly compared to a few years ago, and the game development environment is gradually changing. In recent years, console and mobile devices have become more sophisticated, and our projects have become more extensive. Then, after the pandemic, the way we work has also changed. With the promotion of remote work, being able to work from anywhere has become the norm. Related to this, the shift to cloud computing for online-related services and development environment has also progressed significantly. For Unreal Engine, with the release of UE5, we have been able to create better content by adding features that follow the latest gaming trends, such as world partition, nanite, and lumen. The development environment has also improved. While becoming capable of creating better contents, we have also received a lot of feedback from developers. Spending a lot of time for build on engine code has been an issue since the beginning of UE4. Synchronizing assets, comparing shaders, and launching the editor took a long time, and this was one of the most common issues developers would ask us. We often heard that they took half a day to package the application and could check their game the next day, or they had to do a full cooking and repackaging after editing one asset file. While we are getting better at this, many issues still need to be resolved. In particular, creating better products require try and error. For instance, you might tweak parameters in level design and deploy the game many times to adjust its look and feel. We realized that we needed to reduce wait time in iteration further and improve the engine, because we want the developers to spend more time making their contents and try and error. We have been working on several new features that will improve iteration. In this session, I'd like you to introduce our efforts. So let's get right down to the business. Here is today's agenda. I've already given you an overview, and now I'd like to look at specific features for iteration improvement. I'll discuss amazing, useful features at each development process. Some features are mainly useful for operating in the editor and for checks on the target device. They do not affect the runtime behavior on the application package, so there's no need to take risks. We can try to use some of the features easily by simply changing the settings. So we hope you will be interested in using them. Okay, in this chapter, I'll examine the sync phase and describe virtual asset and the Unreal Cloud DDC. What does it mean to improve the sync phase? Our goal is to speed up the synchronization of the content from source control to the local PC so that you can quickly start working in the editor. Why we need to improve sync? Because we spend a lot of time syncing large numbers of files or huge assets from source control before the developers could start working in the editor. At a high level, virtual asset is a feature that splits asset into two pieces of data to save disk space in your project and improve synchronization efficiency. We released in UE 5.0, but it is production ready in 5.3. The larger the project, the faster and more efficiently you can synchronize data among your team. For more information, please refer to official documentation on using virtual asset. As mentioned earlier, virtual assets speed up the synchronization process by reducing the size that needs to be updated. This feature also speeds up the process by reducing the number of synchronization, and this is especially effective for projects that use various resources such as texture and static meshes. In our tested case of ancient game sample project, the first synchronization saved about 50 times the disk space. A quick explanation of virtual asset is to separate asset in this. This shows the example using a texture asset. Texture asset on the left, which we usually use before virtualization, is divided into two separate assets when converted to virtual asset. As shown on the right, the structural data contains the properties and other data published to the editor and includes the necessary element for an asset. Conversely, bulk data contains information required for display, such as per pixel drawing data. Originally, managing the data in a single file, as shown on the left, had many adverse effects. It was necessary to update the asset whenever properties were uploaded or display data was uploaded. In particular, texture tended to be extensive data, so updates were slow, and the synchronization took a long time. Therefore, we separate the asset to make them to manage easier. To be more specific, here is an image of an operational flow using a virtual asset. This example shows the virtualized texture asset. The user first downloads the asset file, which is the minimum required to use the asset in the editor. Then the texture can be recognized as an asset and used in the editor. If you do not want to edit the actual data of the texture, you can run play in editor. Artists who edit textures directly can check out this file to download the bulk data and update the asset in the editor. Finally, upload the actual data to Perforce by submitting this asset, and the update is complete. In this way, if you don't need the real data, you can read synchronization data on the local PC. Virtual asset is variable, but there are a few things to remember. First, our network connection is required because bulk data requests shared DDC to retrieve data. And you need to use Perforce for source control. If you apply for a new project, please be careful when applying to your project in development. This is because the assets are split into two assets. So if the asset has a problem, you may take time to revert. If the current workflow is stable, there is no need to change. Then, effectiveness will vary depending on the project. The more people involved in the project, the handling of large capacity data and the handling of numerous data, the greater the benefits obtained from virtual assets. On the other hand, in cases handling small data or working with a small team, it is faster to download bulk data locally without using virtual asset. When considering whether to use virtual asset in the project, I hope you will take these points into consideration. Let's now discuss Unreal Cloud DDC. Unreal Cloud DDC is a system designed to efficiently share asset cache data, referred to as DDC among teams. This system provides an accessible, safe, and low maintenance solution that anyone can use. You efficiently replicate DDC across multiple regions and points, ensuring users always connect to the nearest endpoint. For instance, if your colleagues are working remotely from different locations, they won't need to review the data already built by others, nor re-download existing data. This feature significantly impacts remote developer iteration. Efficiently building and syncing DDC facilities smooths remote work. In UE 5.3, it was in experimental status, but in 5.4, it became production ready. Source code and the Docker images are available on GitHub. And we've just tested on AWS, but the system is also available on Azure. If you are considering using Unreal Cloud DDC, start by checking out this documentation available on GitHub. It covers everything from an introduction to testing methods, how to use it locally, and more. This will give you a good overview of the feature. Setting up these features requires somewhat complex configuration and a deep understanding of the backend server. Additionally, it may not be beneficial for scenarios where you don't need to share caches between multiple regions or when working within a small team. So please consider whether your project would benefit from this feature before processing. Although it's a bit off topic, it's deriving to DDC since we were discussing Unreal Cloud DDC, and I'll touch upon it again later. DDC is a feature that cached derived data like resource data for textures and meshes. This is necessary because textures and meshes are initially imported from source files such as FBX and PNG files. Still, the amount of data in these resources data makes loading them directly very time-consuming. Therefore, the idea is to cache the resource part in advance, called the derived data cache. This is checked during loading asset if the asset is cached. If not, create DDC. If it hits the cache data, it is retrieved from the DDC folder. And as shown in the figure, the cache is stored based on the DDC key. As I mentioned, the data to be derived and cached is significant, but the DDC stores this kind of data. DDC mainly contains resource data necessary for rendering, which is acquired at the time of loading assets. For instance, while a static mesh has a large amount of data required for rendering, Megascan assets in particular contain a substantial amount of data. Please note that despite using DDC, there may still be delays in the data retrieval. Now that we have covered the sync phase from here, the next section will discuss improvement in build phase. In the build phase, I'll introduce Unreal Build Accelerator. This feature reduces the build time. Unreal Engine and Unreal Editor are feature-rich, but the source code is huge. This has become a problem because it takes a lot of time to build the engine code. And we used to spend several hours or even a day building it. UBA is one of the solutions that can solve this problem. UBA is a local and distributed C++ compilation solution used in conjunction with the Unreal Build tool and the whole remote build system. As the figure on the right shows, UBA assigns build tasks to multiple PCs and builds remotely. We released UBA as beta version in UE 5.4. It can currently control C++ compilation and jobs on the Windows platform. Mac and Linux platforms are not yet supported. It is limited to distributing tasks on the same physical and private network. There's also documentation on GitHub on how to use UBA. This is a good place to start if you are new to UBA. Let's examine how distributed builds work. This diagram shows the structure and the system for using UBA. The local PC is your PC, and it is the starting point. UBA is required to perform a distributed build, and you can pre-deploy or place your application on the local PC. To perform a distributed build machine is needed to control the distributed tasks. UBA is the application that handles the build tasks, and hold server, hold agent automatically distributes them to UBA. Hold server is an application installed on the build machine. It registers hold agent which exists on the network and collaborates with UBA to distribute tasks. Hold agent is an application installed on remote PCs. It serves as an intermediary between hold server and the UBA, handling distributed tasks on the remote PCs. Here is the flow of a distributed build on this system. Suppose you start engine build on your local PC. It requires a compute task from UBT to the hold server. Hold server receives the request and allocates helper tasks to process requesting jobs. Since remote PCs are pre-registered with hold server via hold agent, hold server allocates helper tasks for the registered hold agent. Here is, the compile agent UBA uploads itself to the helper agent. This allows the remote PC to recognize the build task and distributes the build task from local PC to remote PC. Finally, UBA helps connect to compile agents UBA and assist in compiling. Although this is an example of a distributed build, installing hold server and hold client on the same machine increases the load and the memory consumption of the build process. So we recommend installing only one application, only one machine. Here is the build status using UBA visualizer. This figure shows the distributed build with one local and one remote machine. This shows the build status for each machine with mouse cursors hovering over each task in detail. This allows us to examine the distributed efficiency of the build, as well as any bottlenecks in the compilation. In this way, we can do distributed builds with a simple setup and even include unused old PCs in the agent. As mentioned above about distributed builds, it is possible to distribute shader compilation using UBA. The shader compilation build is currently in beta status, but you can already try it. This has yet to be documentation on how to do this, but I published an article on the forum on how to set up UBA. Sorry, this page is in Japanese, but you can access it using Google Translation. So Scroll builds and the shader compilation have long been time-consuming, and we believe that using UBA will solve this problem. If your project is already on UE 5.4 or you are planning to update, UBA is the way to go. I've told improving about the sync and the build phase up to here. So I'll discuss improving of the cook phase. Cook should be performed when you want to check the operation on consoles and the mobile devices. I'd like to review the cook process a bit. The main purpose of reviewing is to understand the mechanism that can cause bottleneck in cooking. Since cooking accounts for approximately 90% of the packaging process, it is also important for improving packaging iteration. Asset cooking primarily consists of these two processes. In the asset loading process, loading of referenced asset mainly occurs. Subsequently, the amount of the asset savings process is executed, during which serialization takes place. For instance, when cooking the character blueprint, the process begins by loading the blueprint and performing serialization of the U object, which is then saved as a file. Following that, associated assets such as skeletal mesh and animation are loaded and saved through serialization. This process repeats for each asset. This file saving is like an asset conversion. This chart is an example of cooking and converting a text asset. Your asset file on the left is a file that is converted, convenient for efficient in the file handling in the editor. The cook then converts the file so it can be handled conveniently on each platform. For instance, one file converts to 3 files. These 3 files include store package header information, archive information, and resource data. The resource data was accessed using DDC in the editor. But this is not possible in the package, so it is converted as bulk data at cook time in this way. Now let's get back to the introduction of improvements. This is a feature that allows the cooking process to be shortened by performing cooking across multiple processes. This feature allows the cooking operation to be completed faster. It is easy to use as add these settings to the editor.ini file. Once you add the settings, multiple processes will be used to cook when executing cooking from the editor or project launcher. You can use these settings by passing the number of processes as an argument when using automation tool. Here's a figure of 16 process cooking with city sample project, as seen in the task manager on PC. Since I specified 16 cooker processes, 16 Unreal Editor application will launch and all will work cook. Each process will do cook, so we need to have enough memory. In this case, it's a situation where 132 gigabytes of memory is being used in total. Here is the architecture of the distributed part of the merge process. The first process launched creates a cook director at the top, which is a task that controls the entire cook process. And director generates cook worker server processes for the specified number of processes. Cook director communicates with the client about each process via cook worker servers and assign packages for cooking. Cook worker locally cooks the package in each process. By distributing the cooks this way, it is now possible to execute them more efficiently than ever before. This shows the result of multiprocess cooking. I tried to run the multiprocess cooking on city sample and compared the processing time and the memory usage. The line graph showed the effect of increasing the number of processes on the cooking time. But the time increased when the number of processes executed exceeded 8. On the flip side, the memory usage in the bar graph increased with the number of processes. In this case, 4 processes has the best effect, and our project is currently based on 4 processes. Since the effect depends on the project, please verify the actual impact on your project. The next topic is iterative cooking. Iterative cooking is an alternative to full cooking. Full cooking involves cooking every specific package. On the other hand, iterative cooking is parameterized by the result of a previous cook. Each package with cooked output from the previous cook is then examined to determine whether it has been iteratively invalidated. If it has been invalidated, it will be cooked again, just like in a full cook. However, if it has not been invalidated, it will be iteratively skipped cooking, and the previous output for it is preserved. This graph shows the difference in cooking time due to iterative cooking. I cooked twice in a row on the city sample project in this measurement, cooking twice without asset changes, and the cache was compared to see if it would be used. In this case, the iterative cooking completes in 58 seconds. It is approximately 14 times faster. As you can see, iterative cooking is more rapid when the number of changes made to the asset is small and the cache is effective. Today we call it iterative cooking for content changes. In the future, we are optimizing the cooking process to accommodate incremental changes to config and code changes, and avoid recooking at the same data. Iterative cooking works well for small changes, but there are no issue it is not able to handle in some scenarios, such as making changes to Unreal portion of a map file. It is still not fully adaptable to changes in cooking and source code. We are currently working on implementing hybrid iterative for these cases. We are working on the next version of iterative cooking, which we call incremental cooking. This feature will reduce the frequency of false positive in iterative verification. So please stay tuned for our updates. I've examined the iteration improvement features in order. I'd like to focus on the loading app optimizations. The loading times improvements aim to reduce asset loading times. Currently, the number of assets in a title is increasing rapidly as the quality of the game increases. We have been working to improve asset loading continuously since UE4, and in UE5, we are focusing on developing the Zen Series This section will look at Zen Store, Zen Storage, and Zen Loader. I'm going to start by explaining Zen Store, Zen Storage, but I realized 30 minutes ago that I accidentally deleted one page of my slide and submitted it. So I'm missing a few diagrams here, so I apologize for the brief verbal explanation here, and I will also add an explanation of Zen Server. First of all, Zen Store is a function of storing cache. Zen Store indicates where the cache is stored. If Zen Store is enabled, the cache is stored in Zen Storage. Zen Server is an application that manages the cache. Zen Server stores the cache used for iteration improvement in Zen Storage and supports reading to the cache. Zen Server is an executable file located in engine binaries directory as shown in the upper right figure. For Zen Server, only the executable file is included with the engine, and by default, the source code is not included in engine code. If you would like to obtain and modify it from the source code, please visit the GitHub page showing the link. Then Unreal Editor can launch a local instance Zen Server like a civilian process. The configuration determines whether Zen Server is automatically launched by the editor UI process. One of Zen Server's features is its ability to provide several different types of storage services, such as DDC storage layer caching service, and a cooked build server that can use the cooker and the non-shipping game runtime. These services are accessed via HTTP request, but it will be possible to change to other protocols in the future. Second, it is an independent code base that supports all editor platforms. It is built to be an efficient and robust service that can handle billions of requests and achieve high uptime. Let's also look at how Zen Server behaves. This image shows Zen Store acting as a local DDC. When enabled, runs as an alternative to the local file system. This is time-consuming in terms of file I/O performance. Conversely, when Zen Server is running, the cache is stored in memory on Zen Storage, which is better than performance with file I/O. DDC stored on Zen Server eliminates duplication of DDC content across workspaces. This has the advantage of requiring less memory for caching than regular DDC. UI 5.4 introduced the new Unreal Zen Store architecture, which improves data conditioning performance and reduces editor loading and PI workflow times. And Zen Store can be used as both local DDC and a shared DDC. This one is still experimental, but it is available. Building shared DDC through Zen Server requires less chatty network access to remote machine for DDC operations. Also, operations no longer perform synchronous I/O at the DDC store level. Then, editor platform consistency can be provided. The network file sharing mechanism, which tended to vary in reliability across platforms, has been improved and made more consistent. And then Store offered many advantages by acting as a cache server for cooked assets. This feature is currently being introduced as a beta version. First, it avoids writing too many loose files at cook time, thus avoiding a performance bottleneck. When Zen Server enabled, Zen Server can store and manage cooked assets outside of the file system to avoid performance degradation. And you can open the door to efficient network data streaming to the target platform. When running on the target platform, you can facilitate streaming of all asset data via network request to a Zen server instance running on the host workstation. I'd say you might be curious to see how effective Zen server is. So here are the result of my verification. Launch from editor in city sample and compared application launch times and map loading times. For this measurement, I tested on PlayStation 5. Application launch time was improved 1.8 times faster than disabled. Map open time was also significant improvement. Without Zen Store, it took almost 30 minutes to open a map. But with Zen Server, it took almost 3 times as long. The result is that Zen Store allows efficient access to files and reduced load times. Well, this is the last of my feature improvement interactions. We are currently working on improvement to Zen Loader. This feature is not experimental or beta, but a feature in development. Zen Loader is a new synchronous loading system that has less blocking during loading and better file I/O performance. When we released the I/O Store feature in UE 4.26, we released this loader at the same time. To take advantage of this feature, simply enable these settings listed here. These are off by default, but can be made available by adding them to engine.ini file. I want to mention many of these features since they're still under development, but I'll explain with what Zen Loader does better. This profile shows loading the wireframe material in the editor with Zen Loader disabled. It takes roughly 30 milliseconds to load the asset. As you can see, DDC uses a synchronous process to access and perform all loading on the game thread. Until now, asset loading in the editor hasn't been performed asynchronously, and loading in the editor has been particularly time-consuming and interfered with iteration. On the other hand, here is the profile with Zen Loader enabled. The material completed loading in 12.2 milliseconds, almost 2.5 times faster than disabled. If we look at the details of this process, we can see that the processing in the game thread area is now executed asynchronously in asynchronous thread task. In this way, Zen Loader can now perform asynchronous processing in parallel compared to the previous loader, which improves the behavior of the loading process in the editor. Now, let's compare the situation on the sample project based on these results. Okay, so this graph is compared the launch editor time, open map time, and start PIE time, tested with the city sample. The left graph launch editor time was improved a bit, but since launch editor time takes place before the async loader is launched, the effect could be better. The middle graph open map improved by about 1.8 times. We saw an impact of more than 3 times on processing when starting PIE. Thus, now that asynchronous processing is working, we expect to see a significant improvement in the editor's loading time. Finally, here is a summary and a conclusion of this session. If you use these features, I hope you will be able to improve iteration in the editor, work on other tasks, or spend more time adjusting the look and feel of your game. I also hope you have gained a deeper understanding of backend functionality, can find bottlenecks, and you can consider optimal settings on your own. Again, these features are still under development, so I was hoping you could look forward to future updates. Most features are already available in UE 5.4, so we welcome your feedback. That brings me to the end of my presentation. Thank you for your attention.